Hello, fellow programmers. How are you guys? Welcome back once more to this Drive course. And for today, we're going to be analyzing our induction motor parts. We have here on our left just a small diagram, an internal diagram for the induction motor. So as I had previously told you, we have many parts, but these are smaller pieces in which the induction motor, the industrial induction motor is comprised. Now, what do we have here? We have our extractor part. Okay, we have our Voronezh plate. We have the rotor, the axis, the coil, the hull, and the fan. But let's go step by step. Let's go with the most external part possible. Now, what do we have here? We have a fan here, okay? So, independently, we can see it this way. It has a fan system. Now, what is this for? Let's analyze this. Internally, what we need to move, remember, is the shaft in the motor, the axis. Everything that we have here, what we are mostly interested in as drive programmers, is its axis. Why? Because the axis is the brain of it all. Remember here we have the pulley, the refrigeration system, the shaft system. So we are able to move all the big fan in the industrial part. The pumps. We also need the shaft to couple it with our conveyor belt, and that way we can install it. Everything that we need here is in our axis. Now, to be able to run the rotationary motion in our axis, we need to implement a magnetic field in its rotor. Okay? This is the rotor. So further down, we're going to be talking about this. But of all the part, the commutation, the electric commutation, and here for us, so that our motor is able to work in the Voronezh plate. Generally, we are asked for a tri-phased voltage. Okay. Now, since this is a voltage part, we're already starting to work with electricity. Internally, if there were no fan, then all the process that we need to make our shaft turn is going to generate a temperature. So therefore, our motor is going to burn out. Okay? So we may have our coil part, which is burning. So therefore, our shaft has, in the end, the fan that is going to be turning, which is something mechanical, something that the engineers in previous years, they had designed to have a cooling system in its motor. When this is turning, when the shaft is turning at the same time, it's going to turn our fan. Now, this is to cool off our motor. Without a fan, it would internally burn out, and probably our motor wouldn't even work in a very short time. Now, externally, what do we have here? Our hull. Our hull is that device which covers all of the internal system in which the magic happens for our motor, okay? And also, this is also good as this also serves as a cooling system. These lines that we see here, these are known as fins. And these fins are good to disperse the heat externally. So this hull is generally made out of aluminum, and it helps us protect internally our motor. And of course, it is also going to help us protect our personnel in case there's an operator or someone who wants to, for example, touch our motor. If it were at the same temperature in which internally it would be used to move our shaft, we would burn our hand, and it would be a pretty severe burn. So what this is helping us out with is externally it's going to help us have a lower temperature. So that's the hull. Now finally, we have our bearings. These we generally can't see them in the engine, in the motor. But we need to know that if I want to move my shaft, then I need a bearing between the shaft and the rotor. Okay? Now, what are these for? These are so that the shaft can spin freely, and also that is correctly placed around the motor. The bearings equals, for those of you who are looking at this, these are the bearings. Now let's go to the internal working parts. We have our coils, or our coiling, and we also have our stator. Okay? Now, how does this actually work? Well, quite simply, it is a copper wiring that is used around the stator or in its coils. Now, this copper wiring is covered in some sort of enamel. Why do you guys think? As you know, copper is one of the best conductors in the world. Electric cables, logically, or the wires, these are made with copper. Okay, so therefore, this is the #1 internal material used in induction motors to generate a conductivity for the phases or the voltage that we're sending out to the motor. Okay, so that's why it's copper made. But have you ever thought about analyzing why is enamel used for this? Well, basically, from point A to point B, okay, with the enamel, the connectivity with the enamel, there is connectivity with the enamel. If not, it would have to be direct. Because very quickly, as soon as we add voltage in this terminal, it is going to continue its path all the way down the coil. It's going to be progressive. So we're not even going to be able to catch it with our human eye. However, it does do it quite quickly. Now, this generates a magnetic field. If it didn't have the enamel, what it would do is it would go here, and once the coil is already to this point, it's not going to be progressive, but direct, because it's already direct conductivity. So that's going to cause it that it has very little magnetic field, and it's not going to make our shaft turn. And it's actually going to burn out our coil. Okay? It's not really going to make our equipment last. That's why we have our enamel, because it's going to be passing on our electricity progressively. In those turns, all those spins are magnetic field. So that way, it has its desired potency. Now, we have in our stator different coils. Now, they can be 8 coils, they can be 4 coils. Well, these are not very common, but they can also be 12 coils. And each coil, we are going to have to, they're going to have to be wired by copper. What for? So that finally, or in the end, they would have the electromagnetic effect of our rotor. Now, our rotor is that device which is what's going to help us with our motion for our shaft. Okay? Now, this is called, or this type of rotor is called induction cage. Because as you notice, it has the shape of a hamster wheel. Now, how does this work? Okay, we have here. Well, actually, all of this related to shaft motion is summarized as an electromagnetic field between our stator and our rotor. Okay. Now, what you see here on the top part is a coil. So this is a different coil, a different one, and a different one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are 12 coils, which are wired thanks to our copper wire. So that finally, they end up looking something like this. So when we induct a voltage, which in this case is triphased, it is generally going to be internal for the rotor, which it has 2 polarities, the north and south polarity. Okay. Now, each one of these coils, thanks to electricity, is going to generate a different polarity. And thanks to it being 3 phases, they're going to be changing from one coil to the other constantly. Now, during that polarity change, what's going to happen now is, let's suppose that this is the south part of the rotor. This is internal, everything. Okay? And if this is in sub, and let's suppose that this coil for the stator is in north, then in this case it's going to turn. But as I had mentioned, thanks to coiling, the triphased coiling, which is what the motor has, it's going to start changing its polarity. So this is not going to be north anymore. Now this is going to be north. And this polarity is now going to be on this side, which is the same thing. This is not going to be north anymore. This is going to be south. It's going to repel. But now it's going to change it to this side. And so on until it is completely continuous motion. Very quickly though, related to our shaft system. Now, why does it have here these parts here, these strays or these rays? Why are they inclined and not direct? Now, thanks to this effect, what it's going to do is it is always going to be looking for a position, and it's never going to be down. It's never going to be stopped. The situation is never going to be that it maintains in this position, at least not continuously, thanks to its coils, because the field, the magnetic field, is going to always search for the motion, and it's always going to search for or look for the position for the magnet part. So the induction force equals the electromagnetic effect. And that's how the motion is controlled and done. So then in summary, thanks to the wire on the coil in its stator, and all of this is done through the rotor, which is what we ultimately need for it to be turning. It's that shaft motion or axis motion. Now, with this, we already saw all its characteristics for the induction part, for the motor induction, okay, which is pretty simple. So ultimately, for our motor to turn and to always look for its to its position, well, this is the point of view of the rotor. This is our motor shaft. And remember that this shaft motion is what we need, so that we're basically moving all its devices in one line or in one whole plant. Now, what do we need? We need to move the shaft. And what do we need for this? We need all these devices, internal, for the induction motor. Okay? So is that simple? It's pretty simple, right? Now, this topic, believe it or not, is a topic that I got this in a course. I got this through more than half of the course for drives. It makes no sense. It's all about knowing how it works. Yeah? Okay, then go ahead. I don't need to know anything else. If you want to go deeper, that's a different topic, but this has to do with induction motors. We want to know about drives. So therefore, I'm summarizing this practically on how an induction motor works. Now, what's going to continue now is we need to dive into a little bit deeper, but something related to drives, which is the motor plate data. So I'll see you guys in our next class.